So the last section we're going to talk about for this unit is the conic section word problems. So we've dealt with conic sections that are circles, parabolas, ellipses, hyperbolas, and now we're going to deal with some word problems that involve those. So the first thing you want to do with any of these problems is read it, annotate it, and in some cases or most cases, either mark up a picture that's already given to you or create your own picture to represent the problem. That's really going to help with these things. Okay, so I'm going to grab a highlighter here. So an arch in the shape of the upper half of an ellipse is used to support a bridge that is to span a river that is 30 meters wide. The highest part of the arch is 7 meters above the river. And then how high is the arch? 10 meters from shore. And I'm going to really highlight the word shore there. All right. One of the things that is going to be the easiest to work with these is to basically create an X, Y axis so that the center of your ellipse is at 0, 0. All right, that's going to make working with these numbers a heck of a lot easier. Now it says the highest part of the arch is 7 meters above the river. So this part right here is 7 meters. And I'm going to pinch in just so I can reread. Okay, then the river is 30 meters wide. So that's what we want to span. So if it's 30 meters wide, half of it would be over here and half of it would be over here. So this distance is only 15. All right. So now I want to put this together into an actual ellipse equation. So my center is 0, 0. I've got the semi-major axis here is 15. The semi-minor axis here is 7. It's not terribly important that you know which one's the major and the minor. What will be important is that you match them up to the right x and y axis. So we're going to do x squared over, so the horizontal distance here is 15. So I'm going to do 15 squared, which is 225. Plus y squared over the vertical distance here is 7. Whoops, sorry about that. I hate when I do that. So 7 squared is 49, and that's equal to 1. So this equation would model this semi-elliptical arch, at least the top part of it. It actually would have the bottom part, but that wouldn't make any sense, so we would kind of ignore it. It says, how high is the arch? How high is the arch? 10 meters from, and I know the word over here is the shore. So right now, if we look at our picture, the shore is over here. That would be the edge of the river, okay? That's where the bridge is going to touch down. And we want to go 10 meters from the shore, which means I'm going to cut in 10 meters here. So if I do that, right, and I move in 10 meters, that means I would be 5 meters from the center of our ellipse. If I am 5 meters from the center and I'm looking for this height, that point would be 5 with a y. Because I know it's 5 meters from the center, so that's my x value is 5. And height is the part that I don't know. That's the y value I'm looking for. So now using this, I now know my 5 is my x value. I can plug that in and start solving for y. So let's see, x squared, we're going to replace x with 5. So 5 squared over 225 plus y squared over 49 is equal to 1. Let's see, I'm going to grab a calculator here. 5 squared over 225, I feel like that's 1 over 9, but I want to double check. So I know 5 squared is 25. 25 over 225 is in fact 1 over 9. So plus y squared over 49 is equal to 1. So now at this point, I'm going to subtract 1/9 from both sides. 100% use a calculator with this stuff. And of course, I always run out of room. So this whole thing is going to come up here. Sorry about that. So we're going to have y squared over 49 is equal to 8 over 9. So 1 minus 1 over 9 is 8 over 9. I'm doing a quick double check. Yep, it is. To get the y squared isolated, I'm going to go ahead and multiply by 49. All right, so y squared is going to equal, let's see, multiply that times 49. I don't really want it in fraction form anymore. So we're going to get 43.5 repeating. All right, just leave it in your calculator. And I'm going to take the square root of both sides. And y is going to equal plus or minus, let's see what we get here, 6.5. It's a 9, so actually it would be 6.6. All right, so 6.6. Now, one quick thing that I did, I put a plus minus here because when I took the square root and I saw this equation, I am supposed to put a plus minus. However, what I want you to be careful about is, in reality, because we're talking about the height of the arch, the negative part doesn't make any sense. We're not looking at this in terms of this ellipse being underneath the x-axis, so that the negative y values don't make any sense here. So you would just tell me 6.6 meters tall. Okay. Keep in mind that the highest point was only supposed to be 7 meters, so make sure your answer is less than that. If you had done this problem and you got an answer of 18.3, please know that something went wrong in your problem. All right, I'm going to go ahead and slide on down to problem number 2. All right, we have another ellipse problem. We have a racetrack in the shape of an ellipse. It is 90 feet long and 40 feet wide. What is the width 30 feet from the center? So because we can make this ellipse be anything we want it to be, as long as it's 90 feet long and 40 feet wide, I would 100% split this with the origin being your center. All right, that just makes writing the equation that much easier, makes working with the numbers that much easier too. So 90 feet long, we're going to chop that in half and say that this piece is 45. All right. And 40 feet wide means that it's only going to be 20 feet from the center to the top or center to the bottom. So using those two values, let's write an equation. So x squared over 45 squared is 2025, so 2025, plus y squared over 400, that's 20 squared, is equal to 1. So that's the equation that would represent this elliptical racetrack, okay? But we're asked to find what is the width 30 feet from the center. So I'm going to go to the center and I'm going to go out 30 feet, okay? And I want to know this width. So what I'm going to do is, remember, this is now 30 feet from the center. So this point right here is going to be 30x, and just, I don't know what the y value is. So let's go ahead and solve this. So let's see, we're going to do x squared, but x is going to get replaced with 30. 2025 plus y squared over 400 equals 1. I'm trying to write slightly smaller because I always run out of room with these problems. All right, so 900 over 2025. Yes, I'm pretty sure that can be reduced. I'm just going to let my calculator do the work for me. So I'm going to take 1 minus this fraction of 900 over 2025. So let's subtract this from both sides. Make your calculator do the work. Okay. And if you don't have on your iPad yet Desmos or Calculator D4, please put it on there. All right, there is no reason for you not to be working with those. And if you happen to have your own graphing calculator, awesome, use that too. All right, so sliding up here, we're going to have y squared over 400 is equal to 0.5 repeating. I'm going to multiply both sides by 400. So let's see, times 400 times 400. So y squared is equal to 222.2 repeating. Again, I'm just leaving these values in the calculator and just like With this one, I left the 0.5 repeating and I just hit times 400. For this one, I'm going to take the square root of both sides. Whoops, I just took the square root, so there's no more y squared. So on the calculator, I'm going to do the square root of the last answer. And I am going to get 14.907. And there's more decimals, but I'm just going to go ahead and keep it there. Now, you might be tempted to say that that's the width. And I would love to say you're right, but you're only half right. So here's where I'm going to go back to the picture. Okay, and I'm going to zoom in tight on this. What we just found is only from the height from the x-axis to this point. Because I want the whole width, I need to include this distance below here. All right, so I need the distance above the x-axis and the distance below because I want the whole width of the ellipse here. Now, ellipses are symmetrical. So if I had done this correctly, this x-axis here would cut this width directly in half. So what that means is I am going to take that 14.907 and I'm going to double it. So I'm going to multiply that answer times 2. And what you will end up with is a width of 29.814, I believe this is feet, and there is your answer. So keeping in mind that the whole track at its widest point was 40 feet, knowing that this is 29, almost 30 feet, that could work, okay? So the answer makes sense in the context that we have so far. So be careful. In that first problem, we didn't need to double it. In this one, we did. It just depends on the question. All right, so problem number 3, hyperbolas. Okay, natural draft cooling towers are shaped like hyperbolas for more efficient cooling of power plants. The hyperbola in the tower at the left can be modeled by this equation, okay, where your units are in meters. Find the width of the tower at the top. So that's going to be our first answer. And we also want to find the width at its narrowest point in the middle. Okay. And last but not least, the picture shows a tower that is 150 meters tall. And the sides of the tower form a hyperbola opening to the left and to the right. All right. So we already know we have our equation. And our equation has the center at 0, 0. So I'm going to go ahead and split our little hyperbola here. Here's our center, okay? And if we were to need to graph these, we would take from the center and count our transverse axis. We would take 16, take its square root, and we would get an a value of 4. So that's this horizontal distance right here. It's 4. So I'm pretty sure I now know the narrowest point. These two towers, right, the left and the right side of the tower, are 8 meters apart at its narrowest. Okay, it's 4 meters to the left of the center, 4 meters to the right, so a total of 8 meters. All right, so over on the side here, I'm going to put narrowest, and that was 8 meters. Okay, so that part I now know. What I also want to figure out is this distance across the top of our tower. Now, one of the things that it says is the picture of the tower, it is 150 meters tall. So here's the base, here's the top, and this whole thing is 150 meters tall. Well, parabolas and hyperbolas, well, all of your conic sections have symmetry. I just said the wrong one at first. Hyperbolas have symmetry here, so if this whole thing is 150 meters tall, I'm going to chop that 150 in half, okay? So this whole thing is 150, but that means that this height right here, right, from here to here, just the x-axis to that point, would be 75 meters tall. What I don't know is how far on the x-axis I had to go to get to that point. So that point's going to be x, 75. Now, just like I did with the ellipse, I can go ahead and use these two, well, technically there's the y value in this equation and solve for x. So x squared over 16 is equal to 75, whoops, hold on a second, it's not equal, minus 75 squared over 225. Sorry about that. All right, so let's see, 75 squared over 225 becomes 25. So x squared over 16 minus 25 is equal to 1. So I'm going to add 25 to both sides. So that's going to be 26. I'm going to multiply times 16. So 26 times 16 helps if I hit the times sign. All right. So I'm going to go ahead and flip this over here. So x squared is equal to 416. I'm going to take the square root of both sides. So x is equal to plus or minus 20.396. Okay, the minus part's not terribly helpful when we're talking about a distance or a width. But basically that would mean that you actually have the x on both sides. So it's positive 20.396 over here and negative 20.396 over here. So if I want to find the distance between those two, I can just double up the positive value. So if I multiply times 2, so at the widest, okay, which would be the tower at the top, we've got 40.79, let's go 2 meters. And I'm pretty sure that answers problem number 3. With the tower at the top and its narrowest point in the middle. Yes, okay. So we've got the width at the top, we've got the width in the middle. We have taken care of everything for that problem. All right, problem number 4 is the last one I'm going to do in this video, and I will do page 2 in a separate video, just so these don't get to be too long. Let's see. Jake is standing at one focus of an elliptical whispering gallery as shown, and he is 6 feet from the nearest wall. So I'm going to go ahead and put Jake here. I'm going to just put a little J for Jake. And I know that he is 6 feet away from the nearest wall. His friend, and I'm going to be terribly creative and put F for friend, is standing at the other focus 100 feet away. Okay. What is the length of this whispering gallery? For those of you who don't know or who've never heard of whispering gallery, they're kind of these cool rooms where you basically take an ellipse and everything in the room is elliptical in terms of the floor is elliptical, the ceilings and the wall are all the same elliptical shape. And it's called a whispering gallery because if you stand at one of the foci and you whisper something, the person who is standing at the other foci, the other focus point, will clearly be able to hear you, even though you are, in this case, 100 feet away. Because of the way sound waves travel, they would bounce off. So from this focus, they would bounce off the wall and bounce over to the other focal point. It's kind of cool. But what we want to look at and focus on is how we can use these two pieces of information to figure out what is the length of the whispering gallery and then how high is its elliptical ceiling at the center. Okay. So I am absolutely going to chop this ellipse in half vertically, and basically I'm going to put the two foci on the x-axis. All right. So a couple things I notice. I'm going to notice that my center is 0, 0, and from the center to Jake is going to be 50 feet. From the center all the way to the absolute edge of the ellipse is going to be 56 feet. Okay, so that means I would be from the center to the edge 56 feet this way, 56 feet the other direction for a total length. So length is going to be whatever 56 times 2 is. So 112. So 112 is this feet? It is feet. Okay. Now, when it says how high is its elliptical ceiling at the center, what I need you to kind of picture is if this was the edge of the floor and the wall, that if we were to completely rotate it, it would be the same width here. Let me grab a highlighter so you can see what I'm highlighting. It would be the same width here as here on the floor, and all right, you could almost even think of this as like this is the ceiling right here and you're looking at a cross section of the building. Okay, so depending on how you look at it, but that's basically the idea with all of those elliptical whispering galleries. They have to be in the shape of an ellipse. So if we know that from the center to the focus is 50, that's my C value. So C is 50. I know from the center all the way to the edge here, this is my semi-major axis, that's 56. So I know that A is equal to 56. Using the relationship between A, B, and C, which for an ellipse is C squared is equal to A squared minus B squared, I can fill some of this in. Let's see, 50 squared is 2,500. 56 squared is a number I don't know off the top of my head, so 3136 minus B squared. I do a double flip here. I flip B squared over to the positive side, so B squared is equal to, and then I subtract 2,500. It does not matter which order you do this in. Just make sure you get the answer eventually. Let's see, 3136 minus 2,500 is 636. I'm going to take the square root of both sides. So B is equal to plus or minus 25.219. The minus part doesn't make any sense when we talk about distances. So for this particular problem, you can tell me the height is 25.219 feet. Whoops. Do that again. There we go. Since I'm writing right at the edge of the page. One thing with the rounding part is if there are rounding directions in any given problem, follow whatever the rounding directions are. For these, I've been kind of just, messing around with either 2 or 3 decimal places. All right, that's the end of problem number 4. I'm going to go ahead and cut the video here. If you have any questions or concerns,